Hello all. Today I'd like to talk about a subject called stoichiometry. Now it's the first day of the coronavirus shutdown and a man's mind naturally turns to stoichiometry. It's the ratio in which reactants combine to form products, and it's that little number, the molar number, that occurs in front of chemical equations. So that's what stoichiometry is about, and we're going to do an example. But before we can get stuck into that, we first have to look at our BFF, or best physics friend, in this case our best chemistry friend, which is the data sheet. And here I have data for Physical Sciences Grade 12 Paper 2 Chemistry, and then it's got some physical constants. So it's got standard pressure, and it gives it there as 1,013 times 10 to the 5 pascals, otherwise known as 101 kilopascals. And that is atmospheric pressure. That's how heavy the atmosphere presses down on you if you're at sea level. Pascal being a measure of pressure. Then it's got a molar volume, which is given at 22,4 decimeters cubed per mole. Now I'm going to talk about moles later, not those little mammals that go underground, but the chemistry mole. I think people are far more interested in moles that go underground, but that can't be helped. We have to talk about chemistry moles. What it means is if you capture 22 decimeter cubed, that means 22 liters of air. In that air are a certain number of atoms and molecules. And that number is this number, Avogadro's constant, or Avogadro's number. It means that in every 22.4 liters of air or any gas, there are 6,02 times 10 to the 23 individual separate little atoms or molecules. Now I say atoms or molecules because there may be neon occurs as a single atom. It's monatomic. Whereas hydrogen occurs as diatomic, H2 in the atmosphere. Water occurs as H2O, and nitrogen is diatomic. It only occurs as N2. So it doesn't matter whether it's N2 or just neon, Ne, or helium, He. We are talking about there are 6,02 times 10 to the 23 little particles of gas, separate entities, all running around and floating freely and bumping into each other, and they bump against the sides of the container, and that causes pressure. So if you pump that into a balloon, those little molecules are continually moving, doing their kinetic energy thing and Brownian movement and so on, and they bump against the sides, and that all causes pressure, including atmospheric pressure. So the thing that you've got to know before we set out is that in every 22,4 liters or decimeters cubed of any gas at standard pressure, and we're going to talk about and at standard temperature, that means at 0 degrees centigrade, 273 Kelvin. So at the temperature that ice melts, at 1 atmosphere, meaning at sea level with the air pressing down on you, any 22.4 liters of air will contain exactly that number of atoms or molecules in the air. Now, that may not mean too much, but there's another thing that I need to just show you here. If we look at our periodic table, you will see a number at the bottom there, the atomic mass. So for example, for carbon, it's 12. For oxygen, it's 18. Nitrogen, it's 6. Is that 16? Yes, 16. For nitrogen, it's 14, and so on. So for hydrogen, the atomic mass is 1. So that number you need to know. Why? Because if you count out that Avogadro's number, that 6,02 times 10 to the 23, if you count out that number of hydrogen atoms, it weighs 1 gram. If you do that with carbon, you count out 6,02 times 10 to the 23 carbon atoms, it's going to weigh 12 grams. That number there represents the molar mass of each element. So if you were talking about boron, it's 11. So if you count out how many atoms of boron, 6, O2 times 10 to the 23. That means 6 with 23 noughts after it, boron atoms. It would weigh exactly that number in grams. So with that brief introduction to that, we can now begin to discuss stoichiometry properly. And you can always replay this video, so even if there's things you don't understand, we've got now the basics, just the basics with which to solve, say, a very simple little problem. Right, now that we know just a few of the terms involved with stoichiometry, remember stoichiometry has to do with how much of that and how much of that forms how much of that. And normally the how much is reflected by a number in front. If the numbers are 1, we don't write it, but have a look at this. Carbon, let's suppose we have charcoal. And we burn it with oxygen. I think everybody will agree we form CO2. Remember, that's the real baddie, supposedly, for the atmosphere and global warming, etc. Now, let's suppose that I'm going to recklessly have a braai and burn 1 kilogram of charcoal, which is pure carbon. How much CO2 am I going to naughtily dump in the atmosphere? That's the question that I want to solve by stoichiometry. Now, first of all, we've got to know that carbon combines with O2 to form CO2. We've got to know that the formula for CO2 is CO2, not CO or CO3. So let's presume we know CO2, let's presume we know O2. Just count the number of atoms on either side, the left and the right of the arrow. 1 carbon, 2 oxygens, 2 oxygens. That is what we call a balanced equation. So once we've balanced the equation, we now know that 1 atom of carbon will produce 1 molecule of CO2, and it will use 1 molecule of oxygen, or 2 atoms of oxygen. That is the thing we've got to have fixed in our mind. So if 1 will produce 1, then 10 will produce 10. And if we have 6, O2 times 10 to the 23 atoms of carbon, which is Avogadro's number, we're going to produce 6, O2 times 10 to the 23 molecules of CO2. So because stoichiometry tells us it's a 1-to-1 ratio. Now if I go to my periodic table and I look up that atomic mass of carbon is 12 grams of that, and I look up oxygen is 16, 2 16s of 32 grams, will go to form, I could add those two up, 32, 44. We're going to produce 44 grams, which is what 6, O2 times 10 to 23 molecules has a mass of. So see already how useful this is. If we know that the atomic mass is equal to 6, O23, and we know the ratio of that is 1:1, then we know 12 grams of that carbon will produce 44 grams of CO2, but it will also produce what we call 1 mole of CO2. So this represents, 12 grams represents what we call 1 mole, and 1 mole is the atomic mass expressed in grams. Now, also on our data sheet, we saw that 12 grams is also equal to, or if it was a gas, it would have a volume of 22,4 liters. 22,4 liters. We saw that there. 22,4 decimeter cube per mole. So this amount of CO2, 44 grams, represents 22,4 liters of air or CO2. Okay, but we're not going to just have a braai of 12 grams, it's a tiny little pile. Let's instead use 1 kilogram or 1,000 grams of charcoal. Now, if we have 1,000 grams of charcoal, how many grams of CO2 are we going to have? And our most interesting fact is how many moles of CO2? Well, if we know that 12 grams is 1 mole, then what is 1,000 grams? So I think you're going to know how to do your fractions. If 12 grams equals 1 mole, then 1,000 grams equals 1,000 divided by 12 equals, if we have now 83.3 moles, 83.3 moles of that in our brine, we're now going to produce 83.3 moles, 1:1 ratio of CO2 gas. But if 1 mole gas equals 22.4 decimeters cubed, or 1 liter, then 83.3 moles of gas equals obviously more. So let's say 83 times 22.4 decimeters cubed. So let's multiply 83.3 moles by 22.4 times 22.4 will tell us that we now have 18666 equals 83.3 upon 1 times 22.4 equals 186.66 decimeters cubed of CO2. So our barbecue, or our braai, has produced 186 liters or decimeters cubed of CO2 gas. Now that is quite interesting. But let's continue a little bit further. There's something more interesting I want to find out. Because in air, 0.04% of the atmosphere of air is CO2. Only 0.04. So if we had to take that amount of CO2 and spread it into 100% of air, I wonder how much volume of air this actually represents. Okay, let's say if 0.4% is 186.66, then 100% is 100 over 0.04 times 186.66. So let's do the calculation. And that is how many liters of air, that amount of carbon dioxide represents. So if that is 0.4, then 100% of the air, in other words, if we had to spread that into 100% of the air, we're going to end up with 4666666 liters of air. Now, I wonder how many classrooms full of air that is. Well, let's work it out. Let us work it out as how many classrooms full of air would our 1 kilogram braai equal to. The school is building some new classrooms, and each classroom is going to be 8 meters by 8 meters, 8 meters wide, 8 meters long, and let's say 3 meters high. Now, how many decimeters cubed of air is there in that size classroom? Well, in a meter, there are 10 decimeters. So we're going to have 10 times 8 decimeters times 8 times 10 times 3 times 10. We're multiplying each of those by 10 to get them to decimeters. So let's work out how many decimeters cubed of air there is in a classroom. So that's going to be 8 times 8 times 3 times 1000. And so there are 192,000 liters of air in one classroom. So how many liters of air, or how many classrooms full of air does that represent? Well, why don't we divide that into that? Let's divide that into that. So we're going to say 4666666 divided by 192,000 equals. So here's our calculation. 46666,667 divided by 192,000 equals 24,3 classrooms full of air. So our one bry, that amount of charcoal has been formed by plants taking 24 classrooms of air, sucking the CO2 out of that air and turning it into carbon, which we then burn and form into charcoal. So in 1 kilogram of charcoal, the plant had to purify 24 classrooms full of air, 24 standard sized classrooms full of air. Now, isn't that interesting? And we've solved that all by stoichiometry. So I think it's interesting, and I'll tell you why I think it's interesting. Because if we instead bury that 1 kilogram of charcoal underground, do you know how long charcoal lasts? And it does the soil a lot of good. It's called biochar. It lasts 1,000 years. We can actually use the charcoal from plants, bury it underground, and form something called biochar. Biochar is good for the soil because it absorbs humus and compost and fertilizer and slowly releases it back to plants' roots. So instead of burning charcoal, let's suppose we take the charcoal, make it by the normal procedure, and then bury it underground. We can take carbon dioxide, in this case 24 classrooms full of air, if we just bury 1 kilogram of charcoal underground, and it will last 1,000 years. So it's virtually disappeared. This is how we could contribute to sequestering carbon from the atmosphere and then returning it to the earth, where it could stay there for 1,000 years. I mean, that's a long time. So this stoichiometry has got some advantages.